Oi, today's paper is Intelligence at the Edge of Chaos. Very interesting stuff done here. If you've ever been exposed to cellular automata, they use that here to explore what exactly intelligence means, how models develop complex rules, and how generalization works. How can we get a model to train on a data set such that it can actually generalize to more complex downstream tasks that it did not see during training, right? Before we start, remember to like, subscribe, comment, share, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, support me either through Patreon or YouTube. For as low as $1 per month, you can get early access to my videos, or for a one-time payment, hit my Venmo. And if you'd like to borrow my brain for an hour or two, book a consultation call. All links are over on my Linktree. Let's get started. So, traditional methodologies in AI usually involve training models on high quality data sets inherently imbued with human intelligence, aka the full internet for language models, right? And this approach operates under the assumption that creating intelligent behavior necessitates exposure to intelligent data sources. In contrast, this paper today explores an alternative hypothesis that intelligence can emerge from modeling simple systems as long as they exhibit complex behaviors, even when the process that generates the data lacks inherent intelligence. This is getting into like what is the definition of intelligence and all this stuff and like pattern recognition and everything. Kind of weird, I've got to say. It'll make more sense as we go through as to what they're getting at and like the weirdness of the phenomenon that they have discovered. So today we're messing with cellular automata, which if you didn't know, we're going to display them actually in a second, but they are computational models of complex systems consisting of a grid of cells that evolve over time based on simple rules. And the one we'll be looking at today, I'm going to show you a display again in a second. Elementary cellular automata, ECAs, are a type of one-dimensional cellular automaton where each cell has a binary state. So there's just these different little cells, the little data entries, binary state 0 or 1, and its next state is determined by a simple rule that depends only on the current state of the cell and its two immediate neighbors. All right. So let's actually pull this up and get a look at what it actually looks like in case you haven't seen it before. So this is the data that we are talking about. Basically, our starting point is a row of either black or white squares. Think of, I don't know, 1 as white and 0 as black, therefore binary data. And at every time period, every cell changes based off of the conditions of the ones above it. We're going to go down the line. You can see the rules right here. This is rule 110. Not sure what 110 turns out to be, but here, if the three squares above are all black, then we get a white here. So we would end up with these three being a white down here, right? And there's all those rules down the line for different conditions. And so now if we run this, we get a sequence that creates a kind of interesting pattern. In this case, top left triangular matrices, it looks like. Very cool stuff. If you use different rules, you get different patterns. Some are very simple, some are very complex, chaotic, all this stuff. And we're going to take a data set that is composed of this, and we are going to tokenize it in such a way that a GPT can take it as inputs and attempt to predict the next state. And we are going to use that in our experiment. So what we care about is the level of complexity of the output given a certain rule set, right, for these cellular automata. On the far left, we have uniform, class 1. They are just, think of them as the most boring scenario. Center left, in the blue, is periodic, meaning just simple, very, very repetitive patterns, right? And the two more complicated rule sets, classes of rule sets, include class 3 chaotic and class 4 complex. Um, Basically, we will be training models on these different levels of complexity and seeing what they learn and what implications it has for downstream tasks, right? We're going to take models that are pre-trained on one of these classes and then test them on different downstream reasoning tasks. If you look, this left one is pretty familiar to the ARC benchmark. It's made to be just sort of kind of simple logical spatial reasoning. And then the most complex case will have actual chess move prediction. And we're basically checking for a correlation between, depending on what class of complexity the model was initially trained off of these ECAs, how smart can it be at these downstream tasks that are very different. So to generate our actual data, we begin with a randomly initialized vector as the automaton's initial state. That was that top row of black and white squares in the website open. And then we evolve that vector over 1,000 time steps by repeatedly applying the chosen ECA rule. To actually get dataset samples, because there's only 256 unique rules, we actually have to take our huge blocks of simulations and we have to grab random selections from them. So we select random windows of 60 time steps over 100 spatial dimensions, so 100 wide vector and 60 tall as in time step, and we grab that from the initial 1,000 time step uh, total generation, right? And we do this with a bunch of different initial randomly initialized vectors over all of our unique rules that have different complexity levels. And we run that data through a modified GPT-2 architecture, which the only big difference being that it's adapted for binary input and output data, aka the zeros and ones, the black and white squares, right? So instead of using a traditional token embedding layer followed by a softmax over a vocabulary, we replace the token embeddings with a linear projection layer that directly maps binary vectors into the model's embedding space. So we have that initial top row, right, or any of those rows, and it's just a vector of ones and zeros. We run it through a linear layer and we get out what works as an embedding vector, right? So instead of using an actual nn.embedding in PyTorch, we use our initial binary vector and an nn.linear to make it our correct embedding dimension size. And then for the output is a very similar setup to make it binary. We just also at the output apply a linear projection layer to map the model's hidden states, which are vectors of floating points, back to the correct data dimensionality into zeros and ones. I believe getting it from a linear output to actual zeros and ones is just a above 5 is 1, below, or above 0.5 is 1, below 0.5 is 0 type thing. And basically this allows the traditional GPT-2 architecture to handle binary data as opposed to tokenized data. So how do we actually find interesting results that are going to teach us anything about these models from doing this, right? What we do is to evaluate the emergent intelligence of models trained on cellular automata, we conduct experiments on 3 downstream tasks, one easy and one hard reasoning task inspired by the ARC challenge, and a challenging chess move prediction task. So actually think of it as the easy task, the hard one's like a medium task. Chess itself is crazy difficult, is the actual hard task, right? And to make this work, where we're training the model initially on the cellular automata and then using them on these downstream tasks, what we do is we freeze all of the layers of the pre-trained GPT-2 models pre-trained on the cellular automata and train only the input and output projection layers for downstream tasks. So when we go to do these tasks of the arc reasoning and the chess, we actually don't mess with the core of the model, the body of the model itself. We are only allowing to be trained the input and output linear projections that turn from binary data to embedding space. Meaning that we maintain the inherent capabilities of the models, any type of attention head or whatever circuits it has going on are going to stay exactly the same as its initial pre-training under those ECAs. It is literally just the input output layer that are now allowed to adapt to the new data modality. So therefore the model has to figure out how to use pre-made circuits from that pre-training phase on these totally different tasks. And the hypothesis here is that models pre-trained on complex rules as opposed to uniform or periodic or chaotic will exhibit superior performance on downstream tasks compared to those pre-trained on simple rules. Meaning, we are going to train one model on the left side very boring uniform type data of the ECAs. We are going to train one model on the periodic, one model on the chaotic, and one model on the complex types of rule data that are outputted from these cellular automata, right? We have 4 models then, and then we freeze the body, train only the input and output projections, and fine tune those input output projections onto these new downstream tasks. And we see, okay, of the 4 models we pre-trained, which ones end up having better internal in their body circuits for those downstream tasks. With the idea being we would expect uniform and periodic models to do pretty poorly, and whereas chaotic and especially complex to do better because the data structure is richer. To describe those downstream tasks some more, the easy task is a very small, just 3 by 3 squares, and their only thing they're doing is like transformation is a color change, whereas the hard task involves more complex patterns where all transformations are applied simultaneously. AKA, this is the hard task. You can imagine the easy task is if the rectangle had stayed the same position horizontally and only changed color, that would be the easy task. And then they also have the extra super hard, of course, predicting chess task. And now here we can see these are the results, the relationship between downstream task performance and rule complexity. On the left here, we have representative rules that look like the average of that class. So again, here's uniform. That was of the earlier chart, the far left. Now it's at the top right here. These are two examples. Then here are the periodic looking ones. Here is chaotic, and here is complex. We're not going to get too into the difference between chaotic and complex right now, but you can kind of imagine them by their names. Complex is kind of a bit closer to periodic. It tends to have periods of repeating patterns and be just a bit more predictable. Chaotic is pretty inherently unpredictable without actually computing the entire system itself. Then what we're curious about is the relationship between the complexity of what was trained on versus the actual downstream task results, right? So on the x-axis is the complexity of the model was trained on. We have 4 classes here. Again, left to right, uniform, periodic, chaotic, complex. And then on the vertical axis, we have the actual efficiency. Ignore what that means for now. Basically, it's how good was the downstream were the models the downstream task, right? And this first blue is for the easy task, and we can see here that the models pre-trained on uniform rules were the worst, and models pre-trained on complex rules were the best at this easy task, meaning that some of the internal circuits in the body of the models trained on complex ECAs actually were relatively more useful than the internal rules learned by the models trained on uniform and periodic ECAs, right? So there were some internal circuits there that were generalizable outside of the initial data set of ECAs and towards the actual ARC challenge, ARC easy type questions that were very different, right? Moving on, orange is now the ARC hard, the actual transform of the shapes. There is still a positive correlation, but it is not as strong here. And you can see that play out as well in this graph that more clearly identifies which category is which. Still a positive correlation, but not quite as strong as was on the easy task, right? And then finally, when you get to chess, things do get more difficult, but still roughly the same as the complex pre-trained models did perform the best. And we actually see here the chaotic ones dip below periodic, probably due to chess's very rigid nature, I would guess. Not quite sure what's happening there, but you do see an overall trend line that they were in fact correct. Models pre-trained on more complicated data do better when fine-tuned downstream than models trained on simpler data because some of those internal mechanisms learned are generalizable to the downstream task, even when said downstream task is very, very different, right? We do observe explaining this issue with the chaotic ones a bit and their larger variance and doing a bit worse than complex is that models train on certain chaotic rules. They list some specific ones here. All the rules that are possible in these ECAs have designations, are labeled. Models trained on these chaotic rules have poor performance in the hard reasoning and chess move prediction tasks. This behavior is explained due to chaotic systems lacking the structured patterns necessary for effective learning. So this is a whole separate topic. I have a video about the reason why um, transformers and just AI deep learning models in general have so much trouble learning chaotic systems is actually because of some inherent unpredictability, or at least not computationally reducible predictability in the system itself, as well as its sensitive to initial conditions, to where it's just kind of an almost inherently inevitable that these models are going to do worse at chaotic data that I'm not going to get into here, but check out that other video of mine. If you look up on my channel, just chaos, it'll come up, I'm sure. In other words, they may be too random to predict, leading to weaker downstream performance. These results highlight the existence of a sweet spot of complexity conducive to intelligence, where the system is still predictable, yet hard to predict, right? So when learning, when creating intelligence, when creating these generalizable internal circuits in the model, to get the best performance, what you want is not a system that's too repetitive and not a system that's too random, but a system that is in the middle, towing the line between those two. The term they use is the edge of chaos, right? This is true throughout intelligent systems. If you want a particularly more metaphorical, more psychological interpretation or explanation as to why this is the case, even in human brains, and how it relates to mythology and the way humans learn, highly recommend. Actually, I dislike this person in general and all their other work, but I highly recommend this one piece of work by him, Jordan Peterson's old academic book from the 90s, in which he gets into the difference between order and chaos from a Jungian perspective. Very interesting stuff there. Again, I dislike him and all of his stuff since then, pretty much, but that book from the 90s, what was it called? Maps of Meaning, I believe, is really, really interesting and attacks this same problem not from the lens of computation, but from the lens of Jungian psychology. Very cool stuff. The elementary cellular automata are inherently memoryless, meaning the state of the next time point is determined only by the current time point without any consideration of past states. What they're pointing to here is the rules, right? So top row is a previous time step, next row is the next time step. Each of these rules say, all right, the next time step only depends on the single previous time step and spatially only on left, right, and center, right? And it does not, even though you can run the thing and have it generate tons and tons of data, each of these new rows only depends on the row above it. It would not need to see any prior rows, only the single one row previously. That's what they mean by memoryless, right? Now, for each model, a straightforward solution exists. Simply learning the 8-bit ECA rule and applying it to the current state to predict the next state. So what they're saying is, if the model's as efficient as possible, it will just learn these rules, therefore, and meaning it will only pay attention, it will only attention mechanism attend to the single previous state, the single token before it, right? However, alternative solutions may be possible where the model leverages historical states for its predictions. The key question is whether the model is merely learning the trivial solution or if it is integrating information from the state history. So to explore this, of course, they analyze the self-attention scores with respect to the last state in the input sequence and also all prior states. And they do find that the model does in fact pay attention to those far previous time states, at least in some of the complexity classes, right? What that means is even though the system was only determined by the one previous time state, the model is still finding it useful to attend to many previous time states. I believe up to 10, they said. My impression as to why this is happening is because, or my intuition, my guess is why it's happening, is for one thing, the model isn't necessarily incentivized to learn the most efficient solution. It is a statistical model, right? And it can look at prior patterns and just get out statistical averages and things and correlations to get its next guess. But and given that it's over-parameterized, it has no real serious incentive beyond a little bit of weight decay to actually find the most efficient solution. And beyond that, I think what's happening here is that a given model that is trained on one of these complexity classes actually has to see multiple rules, right? There are many different of these rules, and a given model gets exposed to many of the rules in their experiments. And so I think what it's doing is it is using the multiple previous time steps to narrow down which rule it is seeing, and then it is computing said rule. That would be my guess. So it's not actually, under best case scenario, this is my guess, it might not actually be using all 10 or whatever prior timestamps and pulling out correlations and just guessing. it might actually be using those prior timestamps, those many prior timestamps, to find, to actually derive the rule, and then looking at the single prior time step and using the rule on that. But they did not go that far into their interpretability here. I do think that would be an interesting paper to do in and of itself in context learning wise, to see how the model looks at all those prior timestamps and if it does in fact learn the correct rule and apply it on the most recent timestamp. I'm not sure if they released their code, but that would be, if you're looking for an experiment to do, that would be a very interesting one to do. Yeah, I do not see any kind of release of code here. Maybe check out on GitHub if when they do release it. I don't recommend doing that. It's also a simple enough task that you can do this yourself very easily. They do provide extensive information on even down to what PyTorch version they use and everything and all the hyperparameters. So this is very replicable. I recommend if you're looking for an experiment to do, that would be one to do is replicate this and then do better analysis of the actual attention mechanism and try and figure out what algorithm it is performing, because I bet it is very possible that it is using those prior timestamps to derive out the rule and then only looking at the single prior timestamp to apply the rule. Now, they find a strong positive correlation of 0.66 between rule complexity and average attention. This suggests that models trained on complex rules integrate information from past states to make their predictions. So, yes, that's what I was just saying. They do look at the past states. Now, their conjecture here is that the fact that the models are attending to previous states, not just the single previous one, but many previous states, indicates that they are learning a more complex solution to the simple problem. And that actually learning an unnecessarily more complex solution to a simple problem might be what actually makes the model intelligent, aka able to extrapolate onto those arc, easy, hard, and chess downstream tasks. So if the model were to actually have learned just a single previous timestamp, pay attention to that, and use the rule, it probably would not generalize as well. Whereas because it has, bless me, because it has learned an overly complex solution that likely involves multiple different attention head algorithms and everything, that has increased the odds that the downstream task learning on the fine-tuned other dataset tasks are actually doable because it has more to work with in terms of internal mechanisms, internal algorithms. So this concept of computation at the edge of chaos suggests that systems poised between order and disorder exhibit maximal computational capabilities and complex behavior. It's an interesting question as to how do we extrapolate the findings here and the prior work on edge of chaos stuff, and how do we think about how to apply these to LLMs and multimodal LLMs and vision models and etc. Right? Now, to a certain extent, we already do this when we, for example, uh, take our entire internet dump data sets and trim down to only the more useful stuff, right? We are already filtering out and trying to find data that is sufficiently complex, right? And it may be the case that it may make sense. So that prior work we've already been doing for years now on like trimming out bad data has mostly focused on trimming out like low quality data, which I would kind of call more chaotic data in general, as well as just absolutely repetitive data. It might also make sense to trim out stuff that is too complex for the model at this given time point. This is the idea of what's it called? Not continual learning. I know there's a data set called Baby LM that does it, where some people think it makes sense to show these models over the course of their training. At first, simpler data, like the kind of stuff that kids might see growing up, like kids' stories, and then slowly progress until you eventually hit PhD level stuff. I don't think that is done in general in language models today, but some people think it is useful, and there have been some minor findings that it can be useful in certain scenarios. This is kind of the idea here of don't give the model something too complex or too chaotic, right? Keep it right at the edge of what it's capable of. And as its capabilities grow over time, that edge of chaos also moves towards more and more complex behavior and data. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below. For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.